Hello students, welcome back to the fourth video of this playlist. So in this video, we will be solving question number 4 from Pure Mathematics 3, October 2024 paper, which is the most latest paper that is available now. So let's see what's the question number 3 from this paper is about. So basically the concepts from behind this question is from exponentials and logarithms that has been discussed in chapter number 5 of your Pure Mathematics 3 textbook. So in order to be able to solve this question, definitely you should have idea about exponentials and logarithms, and also we need some basic concepts of logarithmic and exponential operations that we have learned from Pure Mathematics 2. So let's get started with question number 4. The number of bacteria on a surface is being monitored. Okay, the number of bacteria n on the surface t hours after monitoring began is modeled by the equation log base 10 n equals 0.35 t plus 2. Use the equation of the model to answer parts A to C. Okay, so this is an equation for the model for estimating the number of bacteria on a surface is given. Okay, fine. So part A here is asking to find the initial number of bacteria on the surface. So initially this is what initially what would be there, t would be equals to 0. So when t equals to 0, what it would be, log base 10 n equals to what, log base 10 n equals to 0.35 times 0, this is what, 0. So this is equals to what, 2. So use the formula to convert logarithm to exponential, which is n equals to what, 10 squared, because if log a n is equals to x, then what, a to the power x equals to n. Okay, so 10 squared, this is what, n equals to 100. So initial number of bacteria is what, 100. Okay, so initial number of bacteria is how much, is 100. That's it. That's what exactly part 1 has asked for. Okay, next is part B. Part B is asking here to show that the equation of the model can be written in the form n equals to ab to the power t, where a and b are constants to be found. Give the value of b to 2 decimal places. So the equation that is given for the model, it is basically in logarithmic forms, right? So we need to just convert this equation in logarithmic form to exponential form. That's the work we need to do here. Okay, so the equation is given as log 10 n equals to 0.35 t plus 2. So what we can write, n, use the formula for converting this formula exactly. We will use this formula. So n equals to what, 10 to the power 0.35 t plus 2, right? So what we can do, we can write 10, the exponential rule, 0.35, since they are in addition, so they can be written in multiplication like this, right? So 10 squared is what, 100. So 100 times what, 10 to the power 0.35. So 10 to the power 0.35 is how much? This is basically 2.2387 something. Okay, that much to the power t. Okay, so what we can write, the value of n can be written as 100 times 2 point, how many decimal places they wanted, 2 decimal places. So 2.24 to the power what, t. So a is 100 and the value for b is 2.24 up to 2 decimal places. That's it. That's exactly what part B has asked for, isn't it? Done. Okay, next is part C. Part C is saying, hence find the rate of growth of bacteria on the surface exactly 5 hours after monitoring began. Okay, so we need to find out the rate of growth of bacteria. So you can easily guess out. We need to what? Differentiate the equation for n. Okay, so the equation for n is what? The equation for n for parts. Oh, sorry. Okay, so the equation for n, it is what? 100 times the exact value, 100 times what? 2.24 to the power t, right? So now differentiate dn over dt. So dn over dt would be what? 100, the coefficient, times what's the derivative of a to the power t. If y equals to a to the power t, then dy, where a is a constant, so dy over dt equals to a to the power t times ln a. Okay, so a to the power t is what? As it is 2.24 to the power t. Okay, then ln what? ln 2.24. Okay, so they wanted when t equals to 5, right? When t equals to 5, so 5 hours after. Okay, 5 hours after, it will be what? T equals to 5. So when t equals to 5, dn, the rate of growth, dn over dt equals to what? 100 ln 2.24, or try to use your the exact value for that, 2.24 times what? 2.24 to the power what? 5. So what would be the value? I have the value for 2.24. The exact value is saved in my calculator, so I'm using that. 100. Okay, so 100 ln answer times what? Answer to the power 5. Okay, that is 2.24 basically. Okay, so you'll get 4531.93 something keeps going. Okay, so they wanted what? They wanted the value up to how many decimal places? Okay, it's not mentioned. Since it's not mentioned, so we can give the answer to the 3 significant figures. Okay, so this is 4530, that much bacteria per what? Hours. Okay, and that's the growth rate of the bacteria exactly after 5 hours of monitoring began. And that's the end of question number 4 from the latest paper, October 2024, Pure Mathematics 3.